So this is a piece of work which we're just finishing at the moment, and hopefully put an archive end of this week or early next week. So I've not talked about this before. I just did the slide on the way down today. So hopefully not too many errors, but yeah, if you do have any suggestions or feedback or improvements, then definitely let me know. We've still got time to try and improve the paper before we put it on archive early next week. I decided to talk about graphs because I've sort of dabbled a bit in graphs over the past couple of years, but I don't get to talk about graphs much. And so I thought it'd be nice to come and talk about graphs for a change. Often I talk about NCMC, and as I was saying to Sam earlier, the problem with NCMC is that you don't get any nice pictures. So lots of nice pictures. My trace plot is nice, but not nice stuff. And some other stuff we've been doing recently, Louis, some of the optimization type stuff I can't talk about because Louis here as well. So graphs is what you end up with. So I hope you like graphs. I'll try and find something which is not MCMC and not with Louis. So this is where we are. Okay, so just to sort of set the scene a little bit about what graphs are. Many of you probably already know what graphs are, but it doesn't hurt to sort of set out the notation. So in this talk, I'm going to focus on undirected graphs. And so a graph is just going to be defined in terms of a set of nodes, which we call V, and edges, which will connect those nodes together. So you get nice and pretty pictures like this. But usually the way we would describe a graph is via the adjacency matrix. So the adjacency matrix looks like this. And if I've done it correctly, what should happen is that you'll have zeros on the diagonal. That's because the graph above doesn't have any self-loops. And it should be the case that if you look at, for example, row 1, it should tell you that the first node is connected to nodes 2 and 3. And it does. Perfect. So what you should notice is that the connections, there's a connection of 1 if 2 nodes are connected, and if they're not connected, so 1 and 4 are not connected, which is why this one is a 0. Okay. The degree of the nodes, that's just the number of edges going in and out of the nodes, and the Laplacian is quite an important object that we're going to talk about later on, is a positive semi-definite matrix, and that's what tells us how heat diffuses across the graph. That's going to be quite an important part of what we're going to be looking at later. So that's the basics of graphs. We're not going to be doing anything more complicated. We're not going to be looking at directed graphs or hypergraphs or anything like that. So it's all going to be quite simple graphs today. But the question is, why are graphs interesting? So the main reason graphs are interesting is because they make nice pictures. But I thought I'd just give some interesting examples of kind of real-world graphs, just to kind of whet your appetite. So this is a co-authorship graph. I think they're all statisticians, if I've done it correctly. And just by chance, we were talking about one of them today, which we did over lunch earlier. Also, I should point these out because he's a Lancaster. But some of these names you might well recognize as statisticians. So the idea is that each statistician is a node, and there's an edge between statisticians who have written papers together. And so what you'll probably notice is that, how do I say this in a nice way? Older statisticians probably have a higher degree to their nodes, so have more edges in and out because they sort of collaborated with sort of more people. Okay, so people who, not suggesting they're too old, but for example, Adrian Raftery, sort of down here, on Gelfand, kind of over here, and such and so forth. So co-authorship graphs, they're really nice. Email traffic, this is actually a directed graph. This is the NMON data set. You might just about be able to make out the arrows. The arrows tell you the direction where the email was sent. And in some cases, you'll see it's bi-directional because, of course, every time you send an email, you have to send them back. So you get replies and so forth, or sometimes you'll forward emails on. Again, another nice example of network. And recommendation systems. If you have a set of users, or say Netflix users, and you have a set of movies, then you can form a network by just looking at the connections between the sort of users and the movies. And this is a bipartite graph because users don't connect to users, movies don't connect to movies. You only connect across from user to movie. Okay. So graphs are kind of cool. It's got more slides. I've got more pictures of graphs. Why not? This is Facebook network. So this is a kind of example of what looks a bit like a stochastic block type model. So you've got some guy, Alex, apparently works at Facebook, and you can sort of see the sort of on his sort of Facebook profile all the different people he's connected to. So he's connected to his wife and his mother, and he's got some family down here, and some church folk over here, and high school friends, and oh, you've got a lot of friends at Facebook. If you have to have everyone, if you work at Facebook, you have to be connected to everyone at Facebook. And it's got sort of fraternity, and so you can sort of see there are these sort of clusters or sort of blocks sort of in the network. It's quite an interesting structure. This is quite cool. Looking at the Connectome project, so these are data sets you can download for free, and they use sort of magnetic or fMRI, I think maybe type scans to sort of look at brain activity in different regions of the brain, and you can map out the sort of connections between different areas of the brain, and you can sort of see that there's a difference between, say, those who have Alzheimer's and those who don't. And so that's kind of interesting. And my last example, I don't know why I like this one. I quite like it. This is a time varying graph. And so this is voting in the US Senate. And so what you sort of have is you have these sort of blobs. This is the Republican blob, all the Republicans voting together, all the Democrats voting together. And what you see, there are some people in between, and you can't quite make up their names, but the blue ones are Democrats and the red ones are Republicans, and they're connected if they sort of voted together on the same bill. Okay, and what you can sort of see is that when you get to sort of the early 90s and Bill Clinton becomes president, it's kind of a change point. You start to see that there's sort of fewer bipartisan connections, and so people tend to, the Democrats will only vote with on sort of Democratic bills, and the Republicans will only vote on Republican ones. And there are just a few senators who sort of vote for both. That's an interesting example of a sort of dynamic graph, which you can sort of look at in terms of sort of change point analysis, which is quite fun. So enough pictures of pretty graphs. So the question is like, how do we actually generate graphs? Okay, so as statisticians, what we would say is, well, there's a simple solution. We come up with a model. So I have a model which I believe matches my data. But the problem is that there are lots of different models out there. So the simplest model you have for a graph is an Euclidean graph. So what you're saying is that when I take that adjacency matrix, zeros and ones, there's a connection between two nodes with the probability, which is just determined by a renewing random variable. But this is the same probability for the full graph, which doesn't seem very realistic. Geometric random graphs is another very simple one, where you just randomly sample some points in a random uniform random variables in a hypercube of dimension d, and what you'll say is that when you sample those lots of uniform random variables, you will form a connection between any two nodes, which is z here, if they're close enough together. So if they're within some radius r, that's a very simple graph. And the last one, which I was given an example of, is the stochastic block model. So this is the kind of graph you want to use, the kind of model you would want to use if you had, say, that Facebook data, where you can sort of see that those communities of friends and colleagues and so forth. And so in this situation, you generate a categorical variable, which is called z. You're conditional on that variable. You'll then draw in connections using a linear random variable, but the probability is determined basically whether or not you are in or outside that community. Okay? So these are all very, very simple. But it's the way that we statisticians would look at it. We have the data, we try and find the sort of appropriate model. And once we have that appropriate model, we can then do frequentists or Bayesian inference to try to estimate the probabilities for these models. And once we fit the models, that's great, because then we can just generate lots of graphs which look like stochastic block models or sort of Euclidean graphs. Okay. But if you were an AI person, you might have a different approach to thinking about how do we generate data, or how do we generate graphs. So many of you probably will have seen this picture, I'm guessing. I think it's one of the most famous dogs in the world. I have no idea what the dog's called. I don't like to know. But this is a paper from a quite famous paper in machine learning on stochastic differential equations and how they can be used for image generation. So how many of you sort of seen this before? Is that of interest? Okay. It's good that you haven't seen it, so I can explain to you. So basically, the idea of sort of modern day image generators is that you take pictures of dogs, cats, happy either way. I personally have a cat, and you take pictures of your cats and dogs, and what you do is you just add more and more noise. So you perturb the pixels in the image until eventually it starts to look like TV static, if you have a certain generation. And I'm TV static, so I'm that generation too. So you keep adding noise to your pixels and you get your TV static. And then the way you've done that is you use usually an alternate Hillenbeck process, stochastic differential equation, to go from data to noise. And because you've used this OU process, you can then work out what is the reverse stochastic differential equation. So if I start just with noise and I want to go this way, I can now create new images just by taking a sample from, say, some Gaussian noise and pushing it through this reverse SDE. And the trick is that you don't know what this score function is, and so you try to approximate it with a neural network. I'm not going to talk about this today specifically. I just want to, but the general idea is kind of similar to what I'm going to be looking at, and this is that you take images or like these graphs, you noise them in such a way that they kind of look like random noise. And if you have random noise, you can then simulate something back out. Okay, and that's not really a million miles away from. Oops, sorry. That's not a million miles away from this, right? Because the way that we generate random graphs here is still a stochastic process. We have some model underlying it, but if we generate random variables, and then from those random variables, we then push those, so the Bernoulli, for example, if we generate these Bernoulli random variables, that's what gives us our graph. Okay, so those are still random variables in the same way that this is creating sort of random data. The only difference really is that we have a complicated neural network, which is sort of doing the work of these kind of simple probability models. Right? So that's what you would do if you were an AI person. So the question is, if you wanted to generate graphs in this kind of generative AI sort of framework, how would you do it? So these are just some random graphs. They're not real, I'll be honest, they're ChatGPT graphs. But they look nice. So you can sort of see that there are different graphs with different structures. And so some look like planar graphs, some look like we kind of got a block structure. And what I'm going to assume is that I have access to lots of data sets of graphs, like this. And this is going to be like my population, my training data set. Now, what I want to know is if I have a set of graphs, then how do I generate more? Things like this. Okay? Now, as I said earlier, if you're a statistician, what you can say is, if I want to have more graphs, first of all, I have to define a model. Once I've got a model, I can generate more and more stuff. That's fine if all the graphs in your data set look like the model. Right? So this is going to break down quite quickly here already, because this looks like a stochastic block model with, say, two communities. That is not a stochastic block model. Okay? So if we have graphs which don't sort of fit our usual sort of simple models, then how can we generate more graphs which are not simple, actually? Okay, so how are we going to do that? Well, one of the approaches that we've sort of taken in this piece of work is to use generators from Markov processes. We're going to go into the details in a minute, but at a very sort of high level, what we're doing is we're taking a graph, which we have here, and you can represent that graph as an adjacency matrix. Okay? So the yellows are like the zeros, and the blue and colorblind, those are ones. Okay? So that means that there's a connection between, say, that node and that node. Okay? And what we're going to do is we're going to find a way of adding noise to this graph such that eventually it will just converge to a set of nodes which are unconnected. Okay? And the way we're going to do that is by using this process, which I'm going to go into details about in a minute. And what I'm going to hopefully argue is that if you can do this, then in the same way you can generate pictures of cats and dogs, you can generate new graphs. Okay? And we're going to do that by taking sort of random noise from this side and pushing it back this way to create a new graph. Okay? So the challenge really lies in this reverse process. So the reverse part is the key bit, so how do you go about it? But in a nutshell, that's what we're going to be doing. And the technique we've come up with is called G3. Generator-based graph generation. Probably overdid the word generation there, but I quite like the idea of G3, so we're going to stop with it. Any questions before I go on?
So it's more like a conceptual question. Like, why do you want to model in one unique model graphs that comes from probably different distributions?
Why do I want to assume there's a probability distribution?
No, like why do you want to run one single model for a set of graphs like the one you showed before that probably comes from different distribution, like an egocentric graph, a graph with different communities? Like, what's the idea behind it?
Yeah, I mean, what you would probably do in practice is you would want to find all the graphs which look the same and train one model. I'll go through in a minute how we do it, but what you would probably do is you would probably not want to confuse too many because it would become hard. So you would take, for example, we have some planar graph later on, so you could just train on planar graphs, and you just train on stochastic block models, and then you can generate more. But the advantage, skipping a bit too far, the advantage essentially is that you're not restricted by that parametric model. So you could have something a bit more non-parametric. So, because obviously the issue we always have with graphs is that the models we have never fully capture real world graphs because you have these issues with degree distributions, you have power law tails. And a lot of sort of like standard models like Erdos many, for example, don't capture those sorts of behavior. So the idea is that we don't need to worry about that. And we'll hopefully show later on is that it's quite simple. There's a neural network in it. I'm kind of skipping people because it's too early, but there's a neural network underneath. The idea is that you have quite a simple neural network and it can actually do a lot of the heavy lifting for you.
But you dump all those graphs in there.
Yeah.
Would this thing just give you a mixture of those things? Is that what happened?
Yeah, in this case, yes. So in practice, sorry, go back a second. Yeah, so in this, yeah, so if you use all of these in your to train your model, as we'll show in a minute, then you'll end up with more that looks like this. If, however, you just focus on, say, these types, which look quite similar, then you'll just get more stuff like those. I think it'd be better to do that. It'd be definitely better to do that. So when we look at molecules later on, molecules can look like this. They have this kind of planar structure. And so we just train on those types of graphs because it's easy to do so. So we wouldn't throw in all the different random ones in which you're not favourite.
Sorry, at the end of all this, you said at the end you got uniform noise.
Yeah.
So is this as if you're prescribing what the inverse CDF is when you go backwards? Is that the
Yeah.
way to think of it?
Yeah, exactly. But then what's happening is that if you imagine the I'm taking on this point. But basically what's happening is when we train the reverse CDF or the inverse CDF, when we train that, what we're going to do is taking snapshots of the forwarding process. So you can imagine when you noise your graph going from this to that, the way it would noise from, say, a stochastic plot model compared to how it would noise from a plane model looks different. And so that's why it makes sense to try and separate them out when you're doing the training.
Sorry, so are you still thinking about defining the model on the adjacency? Because the stochastic process is not the adjacency.
Yeah.
The Laplacian problem.
The Laplacian, yeah. You need the Laplacian. Okay, speaking of the Laplacian, I think that's my next slide. Oh, it's not. I've got almost like. So just, I don't know why I've given you this slide. I put it in my order. But by the end of this talk, what I'm hopefully going to be able to convince you is that if you have a set of training graphs which look like this, these are some enzymes, and those are some proteins, then using our method, this G3 method, you can hopefully create graphs which look sort of similar to the training data. I mean, there is a big, we'll get to this at the end, there's a big question of, does this make sense? I mean, is this actually a sample from this distribution of training graphs? And why do some of my graphs look like horses? I don't know. That's just a nice feature. Okay, so how does it all work? Well, first of all, before we get into the details, I have to talk a little bit about what generators are. So the generator gives us a way to describe the instantaneous dynamics of a stochastic process. So if we have a discrete time Markov process, then we can define a transition kernel. So if we have a state xt and we move forward an extra h amount of time to time t plus h, we have a transition kernel which tells us how we transition from where we are to new states. Okay, that's discrete time. If we look at this in the continuous time situation, then the generator tells us sort of like a sort of time derivative of this Markov process. If you sort of think as h goes to 0, this starts to look like a derivative for some given function. So some function is just any function we choose. We'll choose linear functionals later on for simplicity. But you can imagine the generator sort of tells you the time derivative of this Markov process, or more specifically, it's the generator of the Markov semigroup. Okay, so generators are quite useful, and the reason quite useful is because if you have the generator, it gives you some unique features. It uniquely tells you what your Markov semigroup is. So this is useful if you want to understand what's the finite time behavior. So if I'm at time t and I'm making another 10, 20 sort of steps, what is the behavior of my process in 20, 30, 40 time steps into the future? If I want to know how do expectations evolve through time, this is the Kolmogorov backward equation, then the time derivative of the expectation of this function can be written in terms of the expectation of its generator. It's useful. And lastly, if I care about the evolution of distributions, so if I have, say, distribution of graphs, I want to evolve them in some sort of way, then the generator tells me how that distribution will evolve by the Markov equation. So how probability mass moves through time. Okay. So generators kind of capture a lot of interesting features about a Markov process, which we care about. And we've all seen generators in various guises. So just a couple of examples. So if we have a deterministic ODE, then this U here, the velocity field, this ODE can be written in terms of a generator for some given function. So the function acting on the gradient function acting on the velocity field U here. If you have a diffusion process, you have a drift and a diffusion term, you can rewrite that in terms of the generator against some function f, which is going to be by this form. And if you have a jump process, so if you move from state x to state y, again, that continuous time Markov chain can be defined in terms of the sort of generator. Okay. So, sorry. So generators are quite nice in terms of how they define our stochastic process. And if we look at generators and how they apply to graphs, then there's this really nice connection between the graph of Laplacian, as I just mentioned, and how that can be applied to the adjacency matrix to put heat kernel, or the heat diffusion onto our graph. So, as I said at the start, we have a graph which is G, which has got some vertices and it's got some edges, and L is this graph of Laplacian. So H, this heat kernel, is the exponential of minus the Laplacian times S. S is just time. Okay? And if I apply that kernel to my adjacency matrix, the Y naught is just the adjacency matrix, A. It can be different types of graph representations. So, for example, if you're dealing with, say, hypergraph, you want to use the incidence matrix rather than the adjacency matrix. But for the purpose of what we're doing, you're going to start out with an adjacency matrix, and you're going to apply the symmetric heat diffusion kernel. So this is symmetric in the sense that we're applying the heat kernel to both sides. If we just did this, the most standard way is just to do this instead. So you apply the asymmetric heat kernel, that's also fine. But because we're dealing with undirected graphs, it's more natural to apply this in a symmetric sense. And because we have a collection of graphs, if I assume I have capital N graphs in my data set, what I can do is I can calculate the Laplacian for each of those graphs. I can apply the heat diffusion to the adjacency matrix. This is my adjacency matrix. And I apply, so there should be capital K, so powers of K on these L's to say that this is the Laplacian for that particular graph. And if I let S, this is the time, go from 0 to t, then what happens is I start to add heat and I diffuse heat across the nodes of the graph. Okay? And when you do that, so keep in mind this equation here. If I do that, if I go back, too many slides in this one. This is what you get. So what I'm doing is I'm taking the adjacency matrix here, I'm applying the heat kernel symmetrically, and what you can see is that as time goes forward, so this is the exponential to the power of minus SL, so the Laplacian's fixed, but that S, that time, is going up, up, and up, and as it goes up, you can sort of see that my adjacency matrix has been morphed into an unconnected graph. Okay. So as I was saying earlier, when you look at, I'll go back another slide, if you think about how the machine learning people generate images, it's very much the same forward process that I'm looking at. I'm taking my graphs and I'm heating them up in such a way that they just come to noise. Okay?
Does the graph have to be fully connected to be able to end up at the noise?
Yeah. The graph has to be fully connected to the Laplacian.
Sorry, no. So in the standard diffusion models, right, like they're very data hungry. I mean, but you can make an argument that they're essentially like interpolation functions. But they're of course defined in a continuous domain in each pixel because of the colors. Do you need a similar amount of data, or is the fact that your adjacency matrix is much simpler and that it's binary, does that buy you a lot in terms of the sample size you actually need to make this construction work?
So the advantage that we have is that the way that we're noising, we're using the Laplacian, right? So we're kind of using extra information, let's say, about the graph itself that we are noising. Whereas normally, if you just take this Bob, called Bob, Bob the dog, if you just start adding Gaussian noise, you're not using anything special about Bob's picture compared to a picture of a cat. Yeah. Whereas when we do the noising on the graphs, because we're using the Laplacian, we're using the natural way which heat would diffuse across that graph as part of the noising process. And so when we noise forward, we're using each graph's own Laplacian part of the noising. I think that helps compared to just adding standard Gaussian.
And so therefore you need much fewer data points to make this work in a
instant. Yeah.
Can I ask on that topic then, is there something equivalent in the continuous case in the SD that rather than a 100 OBU, you could do something similar?
Yeah, so as far as other people might know more about this than I do, but as far as I'm aware, people on the forward setting always just tend to use the OU. There are other options that you could do. You're flexible in terms of how you use the diffusion. So people could use other things. I think they generally don't. Part of the reason is because of the reverse process. Because when you do the reverse bit, you just have to approximate this score function. I think it makes it a bit more complicated if you don't use OU, I think. if anybody else. I know more about that one. Okay. Oh, sure. Just look at the clock. Okay, be fine. Might just go a bit faster. Okay, right. So we're going to add noise. We're going to go forward, and so as you mentioned, it has to be a connected graph in order to have Laplacian. And what's interesting is that if you just look at the limit, so remember S is time. If let S go to infinity, what you see is that the heat kernel will then just sort of converge to, excuse me, this rank 1 matrix, where each row of the matrix is going to be each row is going to sort of take the sort of normalized version of the degrees of each of those nodes, and each one of those rows is then going to be the same for all of the rows. So you have one row which is unique, and that's going to be duplicated for all of them. Okay? And what that means is that when you take that heat kernel, you take that limit, which is, let's say, this rank 1 matrix, if you then apply that to ys, so to y0, sorry, my adjacency matrix on either side, then I can actually describe what the limit is going to look like for my particular adjacency matrix. Okay. And what's interesting is that you can actually prove that as s goes to infinity, that this converges to this sort of limiting matrix exponentially fast. And this is really interesting, quite useful for us, because it means that we actually don't need to do many forward noising steps in order to get to our noise or our limiting matrix. In fact, in practice, we only use about 10 or so steps in order to get there. Whereas if you have an image, you might require quite a few steps to take a picture of Bob the dog and make it look like noise. Okay, so we know where we start. We know where we're going to end up in our limit. Before I talk a little bit about the reverse process, one quick thing I need to mention is that in order to sort of connect this a bit with other parts of this sort of literature, especially around flow matching, what we've done is we've rescaled time. So now, rather than having time go from sort of 0 to capital T, we've now rescaled it so time is between, say, 0 and 1. So x0, so time 0, this is your reference distribution, what you're sort of simulating from, so your random Gaussians, let's say. x1 is your data distribution, so in our case, it's a distribution of graphs, but it could be a distribution of images. And what we're going to do is that if y is my adjacency matrix that I've noised forwards, then xt is going to be the reverse of that, so the going backwards, but done so in such a way that it's scaled so that little t is between 0 and 1, okay? And what that means is that x0, how I initialize, is from a very diffuse state, and x1, where I end up at the end, my graphs, is going to be my sort of original graph representation. Now, what you can see is that if you take the time derivative of x, assuming that I use y as this symmetric, if I use yt as being the symmetric heat kernel applied to the Laplacian, then taking the time derivative is going to be given in this form. Okay, so xt is the sort of state of the graph at time t, L is the Laplacian, and t is time. Okay, this matters because this is basically your generator. Okay, so this is the generator. I'll show you the next slide. This is basically your generator for the graph. Okay, so going back a step to when I'm talking about generators. So if you look at the definition of a generator being this sort of time derivative of the expectation, then for some functional f, if I choose that functional f to be linear, because why not, makes everything easier, then knowing that the time derivative of the graph, so x is my state of my graph, is going to be given by this, I can basically show by just some simple linear algebra manipulations that the time derivative of this linear functional is going to be given in terms of A, which is just some real matrix, and the generator. Okay, so this is just the definition of the generator. And so you can basically show that this is kind of like the ODE setting I had at the beginning. I said when you look at generators, you can look at examples as ODEs, SDEs, and jump processes. If you just take the ODE, so this is the time derivative of x, that was equal to the velocity field, that's going to be the generator in this case. Okay, so I can now define a generator for my graph. Okay, and this is kind of the key thing to the whole of what we're doing, really, that we have a generator for this particular graph structure. Okay, but what are you going to do with it? Okay, so we have a generator, but so what? So what we're going to do is we're going to say, well, I have lots of graphs, and for each of those graphs, I can define its generator for that particular data set. Okay, so each graph has its own unique Laplacian, and therefore has its own unique generator, which is indexed by k. Okay. And what I'm going to do is I'm going to learn a surrogate generator. So this is basically going to be a neural network. And I'm going to train this surrogate neural network such that I minimize the discrepancy between what's the true generator and what's the neural network approximation for the generator. So t is uniform between 0 and 1. So I'm going to randomly sample bits of time. Now, why am I doing this? Because when I'm noising forward, I'm getting different snapshots of my graph with different levels of noise added to it. Okay. So I'm trying to train the graph, so I'm trying to train the neural network for the generator to recognize that I want it to be able to replicate graphs which are noisy at, say, time t equals 0.5. Because if it can do that, and it can do it for all t between 0 and 1, then I'll be able to reverse the process and go from noise back to graphs. Okay, and we train this over k, so k is just doing sort of mini batching of the graphs we have in our data set. Okay, and in this case, because we're dealing with graphs, we're just going to use the Frobenius norm as our given divergence. Okay. Now, before we go any further, there's perhaps a natural question, which is, why on earth do you need neural networks? Why on earth do you want this whole surrogate thing, right? Because those who are sort of eagle-eyed might have noticed that if I don't consider the symmetric thing, you can do it symmetrically or asymmetrically, but if I drop the symmetric piece, if I just use the simple heat diffusion, so it's only on one side, on the left-hand side. So y naught is my adjacency matrix, what I started with. I apply the heat kernel, and I let S go from sort of 0 to t, and t goes to infinity. I told you earlier that there's this limiting sort of matrix that you get. But naturally, you might look at this and think, well, actually, why don't I just flip it over, right? So if I know that this ys goes to some sort of limiting matrix, or limiting distribution maybe, can't I just sample some limiting stuff and then just reverse the process, right? That would seem to be a sensible thing. Unfortunately, you can't do it. And I guess it's sort of natural to see why that can't happen, because if you look at the exponential of the graph Laplacian, you're quickly going to end up with numerical instability issues, because when you have certain high frequency eigenvalues, they're going to be magnified exponentially. So this is going to become numerically unstable. So whilst going forwards, it's going to be a contractive process, and this is going to be smooth. When you do the reverse, because you're exponentiating this thing with positive eigenvalues, this thing is basically just going to explode. So this is not actually stable. So you can't just apply the inverse, the direct inverse of the noising process. So essentially, the trick in everything I've just told you is basically that this guy, this generator, when I get this neural network or surrogate, what this neural network and surrogate thing is doing is basically sort of smoothing and regularizing the reverse process. Because the reverse process is ill-posed, and there's actually a paper by Hadamard, 1923, I think I found last week, which basically shows that you can't do the reverse of you can't solve the reverse for the heat kernel or heat diffusion. So what the neural network is doing is that it's acting as a proxy to try to smooth out that instability. Right. So just to give a quick recap from where we are. So I talked about the forward process. I've got some adjacency matrix. I'm going to add some heat, and eventually I'm going to go from a graph down to some unconnected. And now if I've done that, and also when I've done that, I've actually got snapshots of the graph along the way. Because this thing converges exponentially fast, I actually don't need that many of these time steps along the way. But once I have them, the question is then, how do I do the reverse bit? Okay, so I've got my generator. My generator is now being approximated by a neural network. But so what? What do we do with it next? Well, first of all, I need to start with some random initialization, right? Because I don't want to keep generating graphs I already have. I need new stuff. And so how do I get new stuff? Well, I need to find a way of generating some simple Gaussian type noise or uniform noise, some sort of simple noise that I can push through my generator, I'll show you in a minute, push it through the generator, and that will give me new graphs. Okay, but what is a natural sort of initial distribution to sort of start from? Well, as I said, when you go forward, so as you noise the graph, you end up with this rank 1 matrix. Okay, turns out that the rows, the elements of the rows then sit on the simplex. So if you know that your rows have to satisfy a simplex, then the natural distribution to think about is a Dirichlet distribution. Now, this is not the limiting distribution for our process. If I take all my graphs and add noise, you don't end up with a Dirichlet distribution. You end up with these rank 1 matrices. But because they have the sort of simplex like features, using a Dirichlet as like a surrogate initial distribution to start from seems quite sensible. So what we can do is we can sort of simulate columns for our matrix X naught. So this is initialization where we're starting from. So I can generate some Dirichlet random variables, and I can construct what looks like an adjacency matrix by just sort of taking the column of Dirichlets, tap them together, and then add those to the transpose, and then just scale it in such a way. Okay, and then the parameter of the Dirichlet distribution, alpha parameter, basically controls how closely these x naught, these vectors, are going to be to the uniform vector. Okay, so the Dirichlet is really just there as the closest thing which kind of matches where our limiting matrices are sort of going to, but it's not the, well, we can't prove just yet that it's the true limiting distribution. Okay, so I can simulate Dirichlets, that's easy, and I can create some of these like fake looking adjacency matrices, X naught. Then what I would like to do is I'd like to reverse the process. Okay, so if I start with some sort of random noise at time t equals 0, okay, I'd like to be able to evaluate my ODE. So I'd like to be able to use my generator, okay, stick in my X naught, these are my Dirichlet creatures I've created, and then push those through to time t equals 1 to generate new graphs. Now, one of the issues is that, as I mentioned, you can't do the reverse of the heat process because it's unstable. So first of all, we need to have some sort of neural network to approximate our generator instead of the true generator. But also our generator contains Laplacians, and these are the Laplacians for the graph, which means that in order to generate new graphs, I would need to know the Laplacian of the thing I'm generating. So it's a bit chicken and egg. So we can't do that analytically, but what we are doing instead is because our neural network is just approximating the generator, it's basically helping us to avoid the fact that we don't even need to learn these Laplacians anyway. Okay? So we don't need to know the Laplacians because the neural network for the generator is just capturing what the generator looks like on the forward process. Okay? So all the Laplacians that we used were the ones from our trained data in the forward process. When we reverse it, we don't need the Laplacians because that's essentially captured implicitly by the generator. Okay. So now, in order to generate new graphs, all we need to do is to evaluate this ODE. Okay, so we start with some initial data, which is what I mentioned on the last slide, these Dirichlet random variables, construct a matrix, push those through the ODE, which is defined by this neural generator, let's call it, or surrogate generator. And in order to do the sort of forward integration step, we just have to do like an Euler discretization of the ODE, just to make things practical. This is quite straightforward, that's easy to do. And what we do finally is, as we produce these graphs at the very end, sometimes they may not look exactly like graphs. We may not get an adjacency matrix where everything is 0 or 1. It might have values which say 0.99 or 0.02 or something. And so we do a little bit of a projection step just to make sure that the final adjacency matrix is symmetric, it has zeros on the diagonal, and a few other bits and pieces just to make it like a proper adjacency matrix. Okay, that's it. Quite a lot, but that's basically the gist of it. So the whole process has two sides. So there's a train bit. How do you train this neural generator? That is, you take lots of graphs, you noise them forward, you can define their generator under the symmetric heat diffusion. You then get a neural network to approximate the true generator by just minimizing and slowly training. So theta are the parameters of the neural network. You train the neural network so it minimizes its loss. And then once you have this neural generator, what you do is you simulate some Dirichlet random variables, create this initialization graph from those Dirichlet random variables, and then you just push via the generator, you push the samples back the other way, and at the end you get some new graphs. Okay, and as all things which look a bit machine learning, there's a bit of hackiness to it in terms of how we symmetricize and diagonalize and bits and bobs and thresholding. But assuming you're happy to do that, that's it. Okay, so the forward process and the backward process. Very simple. Simple as simulating a neural strategy, I admit, but not terribly hard either. So I think one of the really interesting things, and this kind of comes back to Jeremiah's point kind of earlier, for all the examples I'm going to show you in a minute, we use very simple neural networks, actually. So if you're doing image generation, they use neural networks called UNets, which are kind of like two CovNets sort of stuck together a little bit. They're huge. But for what we're doing, actually, the neural networks that we use are quite small. So we've got 4 layers. This is MLP, multi-layer perceptron. 4,096 nodes. For statisticians, that sounds like a lot, but I guess for machine learning people, it's trivial. Because we have matrices, what we do is we have our graphs, these adjacency matrices, we flatten them, push them through, and the output also comes back as a flattened or vector, essentially, to reshape that into a matrix. And we use Adam optimizer, but you can use any other kind of optimization schemes in order to train the generator. That's quite straightforward. This is an interesting bit. So for the graphs that we have in our data set, they don't all have the same number of nodes. So what we'll do is we look at all the graphs and we find the one that's got the largest number of nodes, and that becomes like the default size for the adjacency matrix. And for any graphs which have sort of fewer nodes, we then just add the adjacency matrix. So essentially we turn those additional nodes into zeros. And when you fit the neural network, you can do this trick called masking. You can sort of hide those parts, so you don't have to learn those parts of the process. Okay. And for a couple of different graphs that we have, so planar, stochastic block model, degree corrected stochastic block model, we're using quite small batches. This is the number of graphs that go in per iteration, so 256, let's say, graphs. There's not a huge amount of data, kind of goes back to Jeremiah's point earlier. We're not using huge graph data sets. The W, that's the number of nodes in our neural network, again, quite small neural networks. T, this is the number of times forward in the diffusion process you have to go. So I mentioned that you converge exponentially fast to the limiting matrix, and you can sort of see that after 6, 20, small number of steps it takes to go from your graph down to this limiting matrix. So the forwarding process is very, very fast. I'm not quite sure to say about this. So what we've done is we've taken our method, which is the top one here. There's also an asymmetric version. So I mentioned that we're applying the heap kernel on both sides symmetrically. If you don't do it symmetrically, the results basically aren't as good. And that's because all the graphs we look at are undirected. And so it makes sense to symmetrize the problem. And for different sort of data sets we looked at, so stochastic block models, enzymes, planar graphs, proteins, we looked at some sort of characteristics of the graphs. So the cluster coefficient, the degrees, there's a number of edges coming out of a node, number of triangles. And what we did was we took the training data set, calculated these metrics in the training data set, so how many triangles are in this graph, and we looked at how many are there in the graphs that we've generated, and then we just looked at the MMD, maximum mean discrepancy between those two things. And these two methods here, default and spectre, these are sort of competing methods which we sort of looked at. I won't go into the details of how they work, but spectre is basically using GANs to try to approximate eigenvalues. The thing which I had to show, because my collaborator Andrew did all the numerics, told me I have to talk about this because it's the most important thing for him. And that's essentially that there aren't many other tools out there that do graph generation at the moment, but the ones that we've looked at, they're all very, very slow. This is the kind of computational time, so time in seconds, for both the training and the generation of new graphs. And so this sort of generator type approach that we have, because it incorporates more structure through the graph Laplacian, it means that training and generation are doing very, very fast compared to sort of many competitor methods. And for some of the competitor methods, when we're looking at, say, for example, enzymes, we couldn't even use this method default because it was in practice it was too slow. So it's quite fast and seems to give quite decent results. Just in my dying few minutes, pictures of pretty graphs. Now, this is the weird thing because you can look at these and you can sort of say, well, that's what the training data looks like, and that's what we've generated. Yeah, okay, that sounds good. Got sort of two communities, there's two communities. And again, got some proteins over there. Is that a real protein? I have no idea. I mean, this is what we generated, that was in our training data set. It's not really clear. And again, for planar graphs and for molecules, again, we took these as our graphs, we noised them, we learned the generator, and we reversed it. This is what we get. Okay, and it looks kind of sensible. We have molecules which look kind of sensible. But I think there's a big question here. It's like, are you generating anything useful? and I actually do not know the answer to that sort of question. So essentially, as I've just mentioned, we're learning generators. That's kind of the main thing I should try to get across, is that using the generator, the Markov process allows us to, when you apply to the natural generator for graphs, it makes this idea of generating new graphs using this process is quite simple, quite straightforward to train. The surrogate, the neural network that we're using, is really interesting in the sense that you can define what write down mathematically what is the true reverse process you should use, but sadly you just can't use it because you have this exponential of the Laplacian, and so it's not actually numerically stable. So the surrogate that we have, or this neural network, is in some ways it's really dealing more with the sort of numerical issues that we face, rather than actually in some of the other sort of literature you see on like score-based methods, where you do actually need to use a neural network because it is intractable to have, say, a score function in the reverse process. For us, the issues are more about using neural networks to deal with some of the numerical issues. The other advantage, of course, is that your neural network is never going to be perfect, and that's kind of good. But if the neural network was perfect, there'd be an issue where you just generate the graphs you already have. So you just take your training data and you generate more stuff that's your training data. But we don't want our training data. We want stuff which we believe is in the population of graphs, but which we haven't already seen yet. It's very fast, and we have probably empirical performance, which is quite nice. Accuracy is really interesting. I mean, I say we have good empirical performance if we look at these MD type metrics. I think there's a really interesting question here. It's quite an interesting statistical question about if you're using any of these generative AI tools, if you're generating graphs or images or whatever it is, how can you say that it's generating something useful? Right? Because you only have the training data, and all you're really saying is that I'm generating stuff which looks like the training, but I don't care about the training. I actually care about the population. I care about, not just about the statistician, but it's not about the sample, it's about the population. Right? So how do I know I'm actually capturing things from the population and not just recreating stuff that's in the sample? So I think that's a really interesting question. I don't know the answer to that. So there's something which we're going to start looking at next. So there are some natural extensions for how we're going to take this further. So you can look at alternative graph structures. So you can look at hypergraphs. Hypergraphs are really useful when you talk about, say, co-authorship. Because if you have, I don't know, say me, Jeremiah, and Louis, if we write a paper together, then if you connect us, so we are nodes, if you connect us by edges, then you'd look and say there's a triangle there. Okay? But actually, we've only written one paper, whereas the graph is telling you that actually maybe there are three edges, so maybe there are 3 papers. The hypergraph separates those higher order interactions. So if there's only one paper, there's a hyperedge, not just an edge. So hypergraphs are quite useful for sort of co-authorship and other sort of similar types of systems. Guidance and conditioning is something we started to look at as well. So if you tell me that the graph has to have a particular types of properties, in the same way that if you have pictures of dogs, I only want my dogs to be black and have blue eyes or something. You know, if I want to start putting in conditions to generate something useful, not just generate stuff, how do we do that? And so that's something we're looking at the moment. And that's my last slide. Thank you.
Time for questions?
Thanks, Chris. That's really cool. I really like this. You just mentioned it like as the very last point before I was going to ask you, like often with graphs, right? The point is that you care about structured data, and so a lot of the graphs you show are fairly unstructured in a way. And I think that's sort of one of the reasons why statistics is not always as relevant as it would like to be for structured data, and why people have really taken up these machine learning. But obviously, one of the drawbacks of these machine learning tools is that you can't really embed a lot of structure into things either. So can you speak a little bit more without revealing any like big secrets that we might steal? How you would want to embed the sort of like hard constraints, right? Like let's say the protein example, like certain proteins that don't bond, that kind of. Is there any way forward using these sort of systems? Yeah. So without telling you the next paper I'm going to write, so just close your ears. But something we have been looking at is if you take the Laplacian, what you can do is you can augment the Laplacian. So there's a literature on spectral clustering. And so rather than just having the Laplacian, you can actually create some sort of latent vectors, and you can attach those latent vectors as additional columns to the Laplacian. It's called, what's it called? Covariate assisted spectral clustering or something like that. And so you can incorporate covariates that you have from the network.
So you're basically adding more structure to the Laplacian, which then feeds into the noisy process. I think that's one way to do it. So in the paper, we have a little example in the appendix. We weren't quite sure if it was going to be in the main paper, just hide it in the appendix. But that's something we just started looking at. The way that they do it in the more standard diffusion sort of world is that they, when you have the reverse process, you have kind of like a classifier type thing. You have like a score function of a classifier, I think, and to kind of direct you towards, cats, must be dogs, or some other features. Maybe we could do something like that. I've not looked at that yet, but incorporating more information into the Laplacian is the way we're looking at the moment. But don't steal that, yeah.
Thanks, that's really interesting. When you are trying to get kind of a tractable target that you can use to train your kind of surrogate generator, I think the way you did it was you stripped like the plus of linear functions, and then the generator through that has a particular definition. Did you think about other kind of classes of functions, and would that be interesting?
So the answer is yes and no. So yes, I thought about it. The answer I only thought about it this morning on the train. So I don't know his answer. I was wondering if I was writing the slides today, I was thinking, you don't have to do linear, do they? I think the linear makes it easier for the theory. There's some theoretical results that we have, and this exponential convergence and so forth. So I think when you go non-linear, it becomes more complicated. But in theory, you can. We haven't explored it enough yet, but you definitely can do it. You can do the generator anyway.
Follow-up, which is actually unrelated. I think the generator you have is defined in terms of the graph Laplacian, so it relates to that particular data point.
Yeah.
Is there anything you carry back over to diffusion as well? So is the analog something like the diffusion process has a drift which depends on a state, rather than just being kind of a...
Yeah, that would be the analog. So the analog, if you look at images or something, it'd be something like that, where when you do the reverse process, there's some aspect of the state conversion or something, which provides structure, because the Laplacian is basically providing structure on the noising process. And I don't know enough about how they do it, I guess, in the image world, if they do anything like that, include like sort of latent variables in the first process, but that would be the into it.
Yeah, sure, fine. Okay, thanks. I'm going to call it conjugate operation, or you call it symmetric, it's a better reason why you want to transpose them. I don't know everything's on symmetric, but I think if you were going to infinite dimensions, you might want to think about making that a conjugate rather than a symmetric product. That's not the question. You're pushing your connection matrix through this process and introducing noise. I guess the canonical decision is that you use the same connection matrix to generate the e to the t a or m whatever to introduce noise. But you didn't have to do that. You could have chosen something that would be sort of canonically let's say off diagonal, one row off diagonal, or something like that. Excellent. Does that play through?
Yeah, so that's a good question. So the heat kernel I have, you don't have to use that one. So something else, another natural alternative, a man walk, for example, the man walk kernels, that's something else. There's a whole host of different ones. The short answer is that there's a lot of the paper, just the one we had, the heat kernel, that's kind of just the heat kernel now. We did look at the man walk, and something else we looked at as well. I think numerically we just didn't get the best results for the heat kernel, why we went down that route. But it is something we're going to look at as an alternative work, these alternative types of kernels. That's a valid walk is a very natural one to look at, but there are lots of other ones. It has to be. There's a really interesting question probably about if you know you have, say, a planar graph, or you know you have a stochastic block model, or such and so forth. What is the more natural kernel forwarding process you would use? I'm not sure the answer at the moment, but yeah, there's definitely lots of options available.
If I understood correctly, you chose your discretization uniformly on 0t essentially.
Yeah.
And,
You don't have to
but
be-
t is an exponent, so I wonder if uniform, let's say, log strings or something else makes. I mean, how does it affect your approximation error?
Yeah, so we just did linear, but I think in practice when people do these diffusion models, they tend not to use linear, they tend to use logarithmic or I forget which one they use, but they don't use linear. We numeric for our numerics we just do linear. I think it's easy to do, but you're probably right that we probably shouldn't, because we do know it converges exponentially fast, and so we probably don't want to use linear. And now you reminded me, I don't know why we didn't do that. I will look into it on the train on the way home. I'm going to try and change it and see what works better.
Se non dà.
My first question is about the experiments. Is this scalable for two very large graph nodes? For example, for protein, some protein pretty large, like 500 nodes.
Yeah, that's fine. So we looked at graph, how much we looked at? Definitely the hundreds, I'm not quite sure if we looked in the thousands of nodes, I can't remember. But for ours, so to be honest, the issue we had actually was when we were coming up with the numerics to put into the paper, the issue we had is that we were trying to compare it to something else. And so we were kind of hamstrung by these sort of computing methods because they don't go very high. And so we could just say, hey, look, we've got millions of graphs, millions of nodes, look at how wonderful our method is. We have nothing to compare it. And so for our purposes, we just looked at some smaller ones.
One question is like for the forward pass, like using the Laplacian, it's like kind of a number of path fields and it might erase the hybrids information very fast.
Yeah.
But not make the reverse process then harder or.
Yeah, and this kind of goes back to Ryan's point as well. This implies you probably need to be a bit more careful of how you do the time discretization going forward. So you probably do want to define the times initially and then space them out more because that would help deal with leisure as much.
And for each context, like deterministic, like it's not like Gaussian distribution, like you analyze it and
Sorry.
We're not that much in Don't insult it. So one thing I was wondering about, like, is whether you can use this, you know, within the existing machinery of stuff that people are trying to solve with the diffusion model. So, like, I'm thinking you have an image, you do edge detection,
Yeah.
which makes the entire thing binary, and it's still a graph.
Yeah.
And then two nodes are connection if and only if one of them is, you know, black, let's say, rather than white. I haven't thought this through, but I was just wondering whether, you know, you've taken some ideas from that space and made them useful for statisticians. Could we use what you've constructed here and go the other way?
Yeah. So I didn't really, maybe I should have mentioned this at the time. So I had this example when I was talking about generating. So generators are linear, right? So you can define a generator which has a deterministic component, a diffusion component, and a driven component. Okay? So if you think about, say, flow matching, that is just this. So you have a generator and you just turn off diffusion, you turn off jump. If you think about the picture of dog I showed, that's diffusion based, and so you turn that off and you turn that off. So this generator formulation is more general. And so the best, I think people are starting to do this a bit more now, start thinking, what's the general setting? Because the general setting is the generator of the Markov process, and then you create special cases just by turning bits off. Essentially. So the answer to your question, yes, it's basically, you know, it fits within that same framework, or they fit into our framework, whichever way you go.
Any last questions from me? Yeah, okay.
Last question about with the mode to generalize well, like this for the graph Laplacian it might be very sensitive to the training set. So when you see like it's possible to generalize some enhancing for some protein or enzymes, which have very, very different structure or different families.
That's a really good question. It kind of goes back to the point I sort of made at the end, like what is good empirical performance? Because what we are generating, we're generating things, and we look at them and we say, well, yeah, that looks sensible, that looks like training data. But you're right, maybe there's an issue that the graph class is putting too much structure. It's forcing you to create things which are too much like what's already in training data. I think probably the way we need to do it, and maybe but something to do probably is just to take our training data and just actually to separate it and just say, okay, well, we've got some bits of our training data which look a bit weird. Let's take the weird bits out. Let's train on everything else, and let's see if we can create those weird things. We probably won't be able to manage it because they're not good training data. But we could do tricks like that to try and see how generalizable the techniques are. I don't generally believe it would be very generalizable. I think we are just going to keep generating stuff which looks like the training. But again, if you knew more about the structure, you can embed more structure through the forwarding process rather than using say Laplacian. If there are other ways of incorporating more information, so I mentioned there's this sort of covariance assisted type stuff you'd use on the Laplacian. If you can incorporate further information that way about the general population you know about, then it might actually be possible to generate more properly new stuff.